Now, first special distribution is the discrete uniform. Now, uniform means that all the probabilities are the same, all right? So all the formulae that we're going to come up with here are for starting at 1, all right? They're for starting at 1. 1, 2, 3, up to n. So if I have 5 possible values, 1, 2, 3, 4, 5, and they are all identical, the probability for all of them should be 1/5. Now, this is the only distribution I'm going to prove the results for E of x and var x for, because it's quite cool and it uses summation notation. Binomial Poisson geometric. Geometric's not too bad, I think, but the derivations are not required. They're not, I mean, they're cool and all, but we don't really have time for them. Okay? Now, a few things we can do. E of x is intuitively should be the middle one. All right? Right? If they're all equally likely, I should get an equal spread of 1, 2, 3, 4, 5s. When I average them out, I should get the middle one. Rara, I'll get the emulator up and I will show you later. All right? But let's just show this. Now, again, I cannot emphasize this enough. The discrete uniforms are in integer values 1, 2, 3, 4, 5, no gaps, 1 to n. The property is 1 over n. Now, E of x then is the sum of, let's go with r equals 1 to n of r times 1 over n. Okay, so the x value times 1 over n, which is its probability. Why am I using r? Because that is a standard summation result in the core pure. That is 1/2 n plus 1. So we do get here, with a bit of cancellation, n plus 1 over 2. All right, which is the middle one. That one being all kinds of tech support. Okay, so intuitively, we think that E of x should be the middle one, but it's quite nice that the math shows that for us. And in the same way, E of x squared is the sum of r squared times 1 over n, which is 1 over n, the sum of r squared. And being the cool kids that we are, we know the result for the sum of r squared. Okay. So var of x is going to be 1/6 n plus 1, 2n plus 1, minus E of x all squared. Let's take out an n plus 1 over 12. All right, because 4 and 6 both go into 12. And now I'm left with 2 times 2n plus 1 minus 3 times n plus 1. That is n plus 1 over 12 times 4n minus 3n is n, 2 minus 3 is minus 1. So in fact, var of x is n squared minus 1 over 12. That result is less intuitive. But it's a really cool use for a given value of cool, right? But it's a really interesting use of those summation formulae that you learn in core pure, those standard summations for r squared, etc. So in our case here, for example, if n is 5, we could work it out from scratch, but we do know the variance should be 25 minus 1 over 12, which should be 2, so much easier. They're quite nice to figure out, these discrete uniform results. I quite like them. Of course I do. Now, I'm going to show a couple of examples of how to muck about this. Sorry, Rara, can you only do these proofs because it's uniform? Yes, precisely. These proofs, these results come from the standard summation formulae, which are you are adding up all of the integers from 1 to n, or all of the integers squared. So you can't have any gaps, and it has to start at 1. So 1, 2, 3, 4, 5, 6, 7, all the way up. Okay, because we are using, this is why I'm showing you this, it's just to really reinforce that the discrete uniform is you are going from 1, or at least these results is 1 to n in integer jumps. Now, there are ways around this. We're going to, what are we doing? We're half an hour in. So I reckon we got time to have a look at a couple of things where we change this around. Let's do something similar. So what if we went, let's start at 0 instead. 0, 1, 2, 3, 4. Oh, and of course, all the probabilities have to be identical. So how would I go about getting the results from this one? Right? So this doesn't start at 1, for example, but that shouldn't stop us. Because much like we were talking about previously about expected values of linear transformations, we can use that quite nicely. We can use that quite nicely. So we shift it. We shift it. So if you compare that to our original transformation, in fact, let's go here. I'm going to use a slightly different letter. What you should see is that y is x minus 1. Y is x minus 1, right? Which does mean that e of y is e of x minus 1. So in our case, it will be 3 minus 1 is 2. All right, and it's still just the middle one. It's still just the middle one. Now, variance is maybe a little bit more tricky. So let's go back a couple of slides and get this result in with the variance one on our previous one. We're not going to show this. What is the variance of a linear transformation? So what is the variance of ax plus b? What's that got to be? Who can tell me that? What is the variance of ax plus b? Yes, Brandon. All right, standard results we need to note, that is a squared variance of x. Okay, the plus b doesn't do anything. So all of these are like how to do linear transformations of variables we need to know. And let's just pop it in here. We might as well, let's have them next to each other so we've got all our little revision keys together. That is a e of x plus b. And we're going to use that. So here, for example, the variance of y is just the variance of x, which is going to be 2. And we can play around with all kinds of things, but if you try and get linear transformations from one to the other, you should be okay. So if we go z, oof, that is a terrible straight line. One fifth, one fifth, one fifth. This looks like it's uniform. We do need to make sure the jumps are all equal. All right, it does need to be uniform. But here z is 2x plus 1. So the expected value of this, now we would expect it to come out as 7, the nice middle value here. So that is 2 times e of x. I think my times there is a little bit too big. There we go. let's go back here. What do we say? E of x was 3. So that should be 2 times 3 plus 1, which is 7, which makes sense. It's the middle one. The more interesting calculation is var of z is 2 squared var of x, which is 4 times 2, which is 8. And again, that times is creeping into big X territory. There we go. All right, but that is the discrete uniform for you. Hopefully my big noggin isn't in the way there.